Hello.
Hello?
We can start, sir.
Yes, sir. Yes.
Yes. Okay. Good evening to all of you once again, and we are, I think, on to the seventh day of this workshop. So I think we have covered uh, a very good amount of basics in Sage mathematics, and we have done a few problems as well. Now the plan is today. I think we had started yesterday with something related to vectors, and I told that today we had to go into some optimization problems, some constrained problems in multivariable calculus like Lagrangian multiplier, and we will be basically focusing on to something related to this computing gradients and Lagrangian multiplier problem and some other problems if the time permits. I guess that we will be having more time after these two problems also. We will try to see. Okay, let me start sharing I have already shared the Google document link. Let me start sharing my screen. Okay, so the multivariable calculus thing we have to define. We usually define functions with variables x, y, and sometimes x, y, z, and sometimes more than three variables. So let us start doing some problems, seeing how to differentiate. Of course, we have seen how to differentiate, and well, let us try to evaluate something called stationary points in the multivariate calculus. And stationary points we will try to see if the second partials test actually tells if the function has a relative minimum or relative maximum at some particular point, or otherwise it has a saddle point at that one particular point. These things we try to evaluate. These things we try to see using Sage mathematics. So the first thing is, let us try to define a multivariable function. So defining the multivariable function, as usual, we need to just okay, let me just take one function f of xy as a two variable thing, 3x square minus 2x star y. Of course, now there can be a problem that y is not defined. So for the sake of completeness, to avoid any doubts in the minds of anyone, I am just defining x also, but x is not, defining x as a variable is usually not necessary unless you have already assigned some other purpose for this x, like suppose that you have given a value x is equal to 5 in one of the previous cells, then it is really necessary to include var x definition here. Okay, defining x as a symbolic variable, that's necessary. Otherwise, if we have not assigned any particular value to this x will be always treated as a symbolic variable by SageMath. That's a convention. 2xy plus y square minus, I'm just taking one function, y square minus 8y. This is the definition. And if you want to see f in the math format, the math print, if you don't want this xy going to, then you can probably write even this. It will be just this. So remember that stationary points for a multivariable function, it means that all the partial derivatives must vanish at that particular point. Then only we say that a point x naught y naught is a stationary point. So that's a definition that we are going to use. If both the partials vanish at that point. Okay, so essentially what we have to do is we have to solve for fx equal to 0 and fy is equal to 0. But the important thing is we need to solve for fx equal to 0 and fy is equal to 0 simultaneously, right? So if you try to solve for fx equal to 0, it can give one answer, and if y is equal to 0, it can give another answer. Now after solving for fx equal to 0 and fy equal to 0, we need to check if if the vanishing points actually are the same or not, or there are some intersections or not in the set of all vanishing points of fx and fy. So instead of that, we can directly use one solve command in which both fx equal to 0 and fy equal to 0 can be simultaneously solved for x and y. So in this way. So these are stationary points. Suppose we name that variable to be this, and solving. So we need fx. Let us find fx here itself instead of doing it inside the solve. F of differentiate f with respect to x, that's fx. Similarly, fy is differentiating x with respect to f with respect to y. And if you want to really see the output, you can even try that. A show command is probably good. Fx, fy. Six x minus 2y. There is no comma. And minus 2x plus 2y minus 8. I think that's correct. 6x 2y. That's correct. With respect to y, it's minus 2x plus 2y minus 8. Correct. So these are the partial derivatives. Now we are trying to solve to find stationary points. So fx, let us equate this with 0. So just see that the space I have given here is just for the sake of what you call ease in reading. So of course you can write this very close to each other. There is no problem at all. But if you give one space around these equal signs, that looks like a little bit better, is what I think. So it's up to you to give a space or not. If you feel that space is not necessary there, you need not. That's it. Fy equal to 0. I usually do, is what I think. Is equal to 0. But now enclose these as these are the equations to solve. Now solve for what? X, y. I think you can give it even this. I don't know whether you need to give it as a list or tuple. Let us see if it's giving some answer. If it's not giving some answer, we will simply change it and print. X equal to 2 and y is equal to 6 is a stationary point. That means that x is equal to 2, y is equal to 6, or 2, 6 is a stationary point, is what solve says. So list of equations. So what we are getting is the points which satisfy simultaneously fx equal to 0 and fy is equal to 0 is computed here, and this is x equal to 2 and y is equal to 6 are the points. There is only one point. Okay, let me update up to this much in the Google Sheet. The link to which I have already shared. The Google document is now updated. You may try to modify inside the solve expression. I have given x y as a tuple. You can try to modify it as a list and see. And similarly, fx equal to 0, fy is equal to 0 is given as a list. You can try to modify it as a tuple and see if that's also working. Okay, so these are the stationary points. Now, we have not seen three-dimensional plotting, but of course we can plot some of the things. Okay, let us try to plot even that. Detailed three-dimensional plotting probably we will deal with later, but maybe we can do something, some little bit of plotting we can probably try. Okay, so for plotting this fxy, essentially what we need is we need the plot 3D command. Instead of plotting, we have plot 3D instead of plot. Okay, the command is quite straightforward. Instead of plot, we have plot 3D. Plot 3D. Now we need to specify the x, y ranges. X within say -2 to. Let us see. After that, if this is not very helpful, if this is not very insightful, if the picture is, we'll try to modify it. Okay, we will keep on adding several things. So shopping. Okay, this is how it looks. I don't know, maybe you have to, okay, y is equal to up to 6 is 6 is a stationary point, therefore maybe we can extend this to 6 or even 10. Something like this you are getting. Okay, you are getting a curve like this. Now the point x equal to 2, y is equal to 6 can be actually plotted. So this is actually here we have already given fxy, and we know that there is only one point. But instead of that, we can actually try to even if there are more than one points, we can try to get all these things and we can try to plot all of them. So we will try to plot those points in a loop. For point in so we need the x coordinate. X coordinate is what? Now pt holds the value x equal to 2, y is equal to 6. So the x coordinate is nothing but pt 0, 0, because there is only, see, this we should consider as pt 0. Okay, this is one point, one solution. So one solution consists of the x part and y part. Therefore this is a single entity, but this is a list. So this is pt 0 because this is already in a list. We are already in a list. Inside that list, this is the list, but this is actually the first entry in that list. Therefore this is pt 0, and therefore x equal to 2 is pt 0 1, y is equal to 6 is pt 0 2. Sorry, again, x equal to 2 is pt 0 0, y is equal to 6 is pt 0 1. Okay, now how will you get the RHS of this x? You need to simply take pt 0 0 dot RHS. This is pt 0 1 dot RHS. That's it. pt. Okay, here pt 0 is not necessary to take because initially pt will be holding only this value. Because we are looping over all the points inside all the stationary points, therefore initially pt will be holding this particular list. So pt 0 dot RHS is good enough. 0 dot RHS. Now similarly y coordinate is pt 1 dot RHS. The plotting, let us move it upward so that we can add to p plus equal to okay. Now one more question is probably here. So here this point, are we going to plot in 2 dimension or 3 dimension? So it's a question to all of you. So what do you think? Suppose we are going to plot this x coordinate, y coordinate. Where will you plot? In 2 dimensions or 3 dimensions?
Yeah. Dimension.
Sorry?
3 dimension, because here we have 3 dimension surface. Actually we have surface.
So what is so we have x coordinate as well as y coordinate. What will be the z coordinate? Can we guess? So if it's a 3-dimensional thing, we need all yes.
The values of x and y in f of x, y.
Exactly. Thank you, ma'am. That's right. So here f of xy will give you the value of z, because we are going to plot the point fxy. So whatever fxy we are getting, that's actually the z value corresponding to x and y. X and y we have already obtained. So this is a 3-dimensional point that we are going to plot. So the point is a 3-dimensional point. So point, that command is good enough. Point. So x coordinate is there, y coordinate is there, and f of these 2 things. But f of these 2 things, we need to be really careful. So we are supposed to actually substitute inside f. There are 2 substitutions we have to make. So we will probably make it one by one. I think that's the correct way. I have not tried that. Okay, we will try this. So f substitute x equal to x coordinate. I don't know whether in the same these things will work. I'm just trying. Y equal to y coordinate. Maybe we can even try to see the point in print. The stationary point is this tuple. Before even plotting, let's try to see this.
Actually, sir, x coordinate and y coordinate spellings where we have defined is different from.
Okay, I got it. Thank you. Oh, the second the second one is actually correct, I guess. But anyway,
Yes.
just take it to be, because it's not spelling is not going to be that serious here. The only thing is that we have to consistently use the variable names. One more is required here. Okay. So stationary point, we are getting 2, 6 xy going to minus 24. But instead of that, maybe we should put f of xy. Okay, 2, 6 minus 24. These are the points. Is this correct? If you put 2 here, okay, that must be correct, I guess. So the stationary point is 2, 6 minus 24. Let us try to plot that point. And the size of the point is going to be very small, so I don't know whether we are in the range of where it is 2, 6 minus 24. Therefore, x and y, yeah, that's fine. X and y going up to 2, 6, we have anyway included minus 10 to 10. So the only thing is the size of the point. If it's very small, we may not be able to see it properly. Size is equal to 50. Giving some color here. Oh, even 50 is very small. I think it's compared to what you call the size of the graph. You can see that there is a point, right? It's very small. Okay, let me just try to magnify it. You can see that here is a point. If we increase it further, what will happen? 50 instead of that, 100. And let us try to change the transparency. I think opacity is the command. As it becomes somewhat transparent, I guess so. Let us try to increase that transparency. Oh, I am decreasing the transparency or what? I don't know. 0.2. But it doesn't seem to have any effect, right? Okay, let me just see. I think opacity I should probably apply inside. Oh, sorry. Opacity I am applying in this point.
Yes.
Sorry. That's not the thing that we wanted. We wanted it in P. It's too dull. 5 is good enough. But in that case, black is better because that has better catching color of, yeah. You can say that the point is there, point is here. Okay, the point is anyway here. So we see that how to find out the stationary point, how to plot it, all these things we have done. Okay, let me just update the Google document with all these things so that you can try this. I have updated the Google document with this. So that if you click on this picture, if you click on this picture and hold the mouse and try to rotate, it will offer rotation. So one small issue can be there. It depends on the kind of system that you are in. If you are using an old version of Sage, there are certain issues with this three-dimensional plotting. Maybe you have to give an extra command like viewer, which viewer to be used by default. The default viewer may not work, therefore you may have to specify the viewer. Sometimes it may be necessary and sometimes it may not be necessary. Sometimes you may have to just select viewer. Sometimes it's necessary. I'm not very sure about your system. This command is sometimes used. 3JS. That's a kind of viewer available with Jupyter. When the default one is not working, probably you can shift to this. I don't know whether whether the default one as of now is 3JS or not. Anyway, in my system, without giving any specific viewer, it's working. That's the only thing I know. So from this graph, probably you can make a guess that the point that we have taken. So you can see that desert, if you are going upward, it's increasing. Therefore, the value we have chosen, this 2, what is that point? 2 minus 26 or what? 26. You can see that this 26 is nothing but its relative maximum or minimum. What do you think from the graph?
Sir, can we draw a tangent surface?
Sorry?
Tangent surface. Can we draw a tangent? Can we draw the tangent surface?
Provided that we know the equation, we can draw anything. But it's up to us to precisely define that, because here we are actually drawing a surface here itself, right? So f of xy is a surface and we are drawing it using plot 3D. The equation of the tangent surface we have to locate. That's the only thing. Anything can be done, but see, SageMath is actually a software that gives you a set of commands, set of software packages for doing whatever you actually want to do. But the thing is that we must know what exactly to be done, right? So the mathematics behind that, Sage cannot help us. So many of the problems that we are trying to discuss may not have by default a package in SageMath. May not exist a package for drawing tangent surface, but we can draw them, provided that we can understand what exactly we want to draw, what type of surface we want to draw, and what is the equation of the tangent surface. Tangent surface essentially means that it's going to be a plane, right? Tangent surface is essentially a plane. Instead of tangent line, we are drawing a tangent plane in 3 dimensions. So the equation of the plane we must be able to find out, and so what are the extra things that's required for finding out the equation of the plane, we should know. And when do we call that to be the tangent surface, there also we should know. In the case of tangent line, we know that we are constructing a line where the slope of that line is equal to the derivative value of the derivative at one particular point. So slope is known, equation of line is known, so we can draw the tangent line. But here, if you know the tangent surface equation, if you know the slope of that thing, here also we will be able to do. We'll try to see that. I don't know whether I have included that in that. I have not planned anything precisely. Initially, what I have in my mind is go to this Lagrange multiplier problem, and after that we will see. Of course, we will keep it that in mind and we will try to do that. I don't I have not gone through the equation and the mathematics behind that. See, if you know the mathematics, we can of course try. Okay. Yeah. So my question was this point, this relative extrema, is it a maximum or minimum? We can see that Z is going, the surface is going upward, right? The surface is going upward, and we can see that this point is actually lying somewhat below. Therefore, we can probably guess that this is going to be a local, it's a minimum, right? Because we are seeing that it's on the very bottom of the curve, and everywhere around the points are going upward. Okay, the points are going upward. So we can probably guess that this is a local minimum. So anyway, we need to actually conclude that using mathematics. So for concluding that, we need the second derivative, second partial test, which essentially says that we need to evaluate fx, fxx, which is the second derivative with respect to x, and fyy with respect to second derivative with respect to y. So fxx x naught y naught into fyy x naught y naught minus fxy square x naught y naught. If that is so I will just try to give that definition here, second partials, or maybe even I can open here something. Second partials test for local extrema. So this is essentially the test we have. So this hxy is fxxy into fyxy. See that when we have continuous partial derivatives, this fyx and fxy are going to be the same. Therefore, fyx into fxy we can take it to be fxy square xy. So fxxy minus fxxy into fyxy, that's what the determinant is. And minus fxy xy the whole square. This is d. Okay, d is defined to be this. So we don't have to define it as a matrix, but instead of that we can simply take the product of these. Now, if AB is the critical point, which we called to be a stationary point, if AB is the critical point, what we can see is if depending upon this D value and fxx value, we can say that if it's a local maximum or local minimum. This is what we are going to use. If it's less than 0, it's a saddle point. That's the definition. And if it's equal to 0, if D is equal to 0, the test is inconclusive, therefore we cannot conclude anything. So essentially we have to take this, right? We have to take the determinant of this, fxx into fyy evaluated at xy minus fxy square evaluated. Okay, this is what we are going to do. Using second partial test. If is a relative so each and every point we will do. So we will do it in a loop. So what is it we have to calculate? We need to calculate D equal to a second derivative, right, of f with respect to x. F with respect to x 2 times and evaluate it at x equal to x coordinate, y equal to y coordinate. So second derivative found, evaluated. Now this is with respect to x. Now we need with respect to y. The same procedure. Now minus, I'm breaking the line. Minus what I'm supposed to do. So differentiate with respect to x first, and then now I need to probably apply the derivative differentiation command 2 times. X first and y first. Y next. Y. So fxy, the 2 derivatives are found. So square of that. So what is the value of D? And what is the value of fxx? So evaluated using fxx. Fxx value, which is we already we have written a code for that. This is it, and your y value is so here. That's not required. Fxx is enough. Fxx and D is enough. So this is fine. One bracket is missing. Let's see. I think basically here, because I am using fxy, instead of notation in this fxy, I can simply use f here. No need to use fxy. Everywhere I can simply drop that fxy. I think this is good enough. Fxy I'm dropping. Here also. That's why this xy going to is appearing everywhere. D is 8, fxx is 6. So both are positive. So what is the conclusion? This is positive, this is also positive, therefore it's a local minimum. If it's positive and if fxx value is negative, then it's a local maximum. Therefore the conclusion here is if what should we say? D greater than 0 and this value greater than 0, we will say that it's a local minimum. That's what we want to say. Otherwise, so this is general technique. So we will write the complete code. If this is less than 0, local maximum. And what is the third one? If it's less than, this is D itself is less than 0, there is nothing to, it's a saddle point. And else, the final case is that the test is inconclusive. This is the final thing. Sorry, I will just remove this command, which is not necessary in my system, may be necessary in some systems using some old version of Sage, and even using Sage in Windows. I don't know what exactly the case is. This issue was there for Sage 8 versions, if I remember correctly. So I'm updating the entire program in the Google document. As previously, there are indentation issues by copying and pasting the code to Google document. So please be careful that if, elif, etc. are not, the contents inside these conditionals are not properly aligned. Okay, I think this problem is somewhat alright for everyone.
Yes, sir.
So to plot the tangent surface, what is actually the equation of the tangent that tangent line? Sorry, tangent surface. Is there any specific equation for that? I don't actually remember what exactly it is. So if there is an equation, please find out the reference and give it to me so that we can try to do that problem. If there is some Wikipedia page or any other mathematics page which gives tangent plane equation, not tangent surface, I think tangent plane. So we know that for constructing the tangent line we have slope, but here what exactly we are supposed to do for finding tangent surface? I think we need to find a normal, right? Normal to that surface. Then the plane perpendicular to that normal vector. That's what we are supposed to do, right? I think
Yes. Yes.
I think something like that. Okay, I think I found one link from somewhere here. One of you can probably see if this link is correct or not. If it's if this is exactly the same thing that we have in your mind about tangent plane. If this is exactly the same thing, we can easily plot this tangent plane. But this is not actually directly using. Okay, they are also using that only, that vector notations only, but they are converting that into partial derivatives, and they are converting it into something which is much more easy to understand. But easy to understand. Okay, I think we will do some vector calculus, and after that we will try to do that, because constructing the normal vector, after constructing the normal vector, using that normal vector to construct a plane, I think we should do that problem. If you proceed like that, then it's going to be much more interesting. Instead of directly depending upon a ready-made formula, we can try to use the vector calculus to arrive at that thing. Okay. Okay, now we will try to do one problem that, as I told in the beginning, that Lagrange multiplier problem, because this is a problem that we have already mentioned. After this we will probably come back to this tangent thing, so if the time permits, otherwise we will keep that in mind. So Lagrange multiplier technique, I hope that you are familiar with. I will try to share a page from where we can probably find all these things. So once again, Lagrange multiplier technique, it's here. So going to Wikipedia once again. So what essentially we are supposed to do is, okay, we'll try to see one problem itself here. So suppose that we have essentially the problem is that we are trying to maximize one surface. Okay, we are trying to find maximum value of on a surface, but with respect to certain extra condition. We want the maximum to occur at a curve on that particular graph on surface. Okay, instead of the absolute maximum, we are not trying to look at an absolute maximum or anything like that. On surface we want a maximum, but the maximum needs to be subject to something which is most probably going to be a curve on that particular surface, and on that curve we are trying to find the maximum. That's what essentially we are doing. So the problem looks like maximize or minimize sometimes. Since maximization of fxy is the same as minimization of minus fxy, so maximization is good enough to understand the problem. So maximize fxy is subject to this, and so for that what we essentially do is, I'm not going into that detailed theory of that thing. So for that what we essentially do is, we will try to solve something called a Lagrange multiplier equal to 0, which is fxy minus lambda xy, the gradient of that taken equal to 0. This is what essentially doing. So we need to find out, we need to know what exactly the gradient is. Okay, I will try to explain the things in between. So the essential things, let us collect each and every essential thing first of all. The first thing we want is to find out the gradient of a function. Okay, and one more thing is, okay, we will start doing the problem itself. This is a problem taken from Howard Adams' calculus book. And the problem is that, suppose that we have the surface x square plus y square plus z square equal to 36, which is a sphere with radius equal to 6. Now, what we are trying to do is, we are trying to find a point on this sphere which is closest to the point 1, 2, 2. Okay, I will try to define that function first. While going through this problem, we will try to see the basic things, the basic concepts inside this problem. So the problem is this. Constrained optimum on surfaces. So define f equal to, the problem initially is that a point is given to us 1, 2, 2. Okay, we are randomly choosing a point, say it's 1, 2, 2. Now a sphere is also given to us. So we are trying to find out the distance from this point to all other points. Okay, then we have a distance function from where we have a distance function from 1 to 2 to any other xy. So how will we write that distance function? We know that the distance from 1 to 2 to any other xyz is nothing but x minus 1 the whole square plus y minus 2 the whole square plus z minus 2 the whole square, which is the distance between xyz and x naught y naught z naught is nothing but x minus x naught the whole square plus y minus y naught the whole square plus z minus z naught the whole square. That's the distance formula, square root of that. Now, instead of finding the maximum, because the maximum we cannot definitely find out, because when we are moving away from this point 1, 2, 2, the distance naturally increases, and the maximum is nothing but infinity, and the minimum is of course equal to 0 at 1, 2, 2 itself. Therefore, we are putting an extra condition that we want to maximize the distance from this point 1, 2, 2 to xyz, but this xyz has to be on the sphere x square plus y square plus z square equal to 36. That's a constraint. Okay, so we have two functions now. One is the distance function, and we are trying to maximize that, subject to the condition that the maximum of this function we want on the sphere. It's not essentially a curve on the sphere. What I told is not completely correct. So this is just a constraint, not necessarily a curve on the curve. It's just a constraint. This constraint actually connects this this function, the original function, and the point where we have to, the point where we are, point which we are trying to locate. So essentially, we are restricting our focus to a subset of R3, and inside that subset we want to find out a maximum or minimum. That's what we are trying to do. Okay, so let me define two functions. F is distance. So arbitrary a point is given. There is no specific reason for choosing this point. Some point is chosen. F is distance from this point to x, y, z. maybe to avoid certain complications, we can, to simplify the function, we can assume it to be the distance square. So maximizing distance function or the square of distance function, both are essentially the same. Because we are choosing the distance, there is no negative values accepted, therefore we can maximize or minimize the square of the distance function. This is the problem. Maximum of f on a sphere G. So this is essentially the problem. So I hope that the problem is clear to all of you. So here the surface is nothing but G. Maximization is that of f. So we need to find the maximum on G. Okay, let us define f. X equal to, as I told, x minus x naught, y minus y naught, z minus z naught, all these squares, and a sum is taken. X minus 1 square plus y minus 1 square plus z minus, sorry, y minus 2, 1, 2, 2. Okay. Z minus 2 square. This is the f function. Now g function we are choosing to be the
Sir, is it not necessary to increase the variable?
increase what?
Is it not necessary to increase the variable? Variables.
Means what?
So variables are not increased. We are using y and z. So
Right. X, Y, Z I am using. Okay. All right. Thank
variable
you.
x, y,
Thank you.
z.
Thank you. That's correct. That's correct. Otherwise, it will throw an error. X, Y, Z. Correct. Sorry. Yeah. So it's necessary. Yes. X, Y we have already defined, but still it's better to just do it inside that cell itself once again. There is no harm. You will be safe. G equal to now the sphere x square plus y square plus z square equal to 36. That's a sphere that we are trying to see, but instead of that we will take minus 36. That minus 36, okay. So G is taken to be the surface, F is taken to be this the distance function. Okay, let me update the Google document with this. The Google document is updated with all this. Okay. So we have done up to here. Now the technique after this remaining is, now we are supposed to find the gradient of f, gradient of g. Both these gradients we are supposed to find. So we need to know what exactly the gradient is. We define the gradient to be a gradient of a function f of xy is the vector fx, the partial derivative with respect to x, fxi plus fyj. That's the gradient. Okay. So if we have a function, so let us see the gradient of f. So it's f grad. Let's write this as notation. So computing gradient is quite easy. F dot gradient, that's it. Show F gradient. And if you ask to type it, the type of it, you will get it as something very complex thing, free module, etc. So it's not actually treated as a vector, but it holds the properties of vector, it seems. You can see that later. So show F gradient. Now computing the G gradient also similarly. Now let us go back to the theory, which tells us what exactly Lagrange multiplier do. So essentially, we are supposed to take a gradient of f. Okay, where is that? I'm not seeing that the simplest interpretation. Yes. So here we have fx okay, gradient, where is it taken? So essentially what we are trying to do is we are trying to take the gradient. Okay, I will just use it from the textbook and once again. So we are trying to solve for, we are trying to now solve solving f gradient minus some variable L. So we need to define it as a variable once again. L into G gradient equal to 0 4 in terms of x, y, z. That's a technique now. So what is L? We don't know what exactly this L is. Anyway, we will try to use a symbol called L. That L is not very important for us. Just let us try to see. So I need a better description about this gradient, Lagrange multiplier, so that I can show it to you. One second, let me see if I can show you something. Okay, maybe probably I got a better link, a better place where I can get some, I can show something related to that. So essentially we are trying to solve this. This is what we are trying to do. Gradient fxy equal to lambda gradient gxy, that which means that the gradient of f and gradient of g are scalar multiples of each other. That's what essentially it means. Scalar multiples of each other, and what scalar multiple, that's not very important for us. Okay, so we are trying to solve this first of all. That this del fxy gradient minus lambda del gxy equal to 0 is what we are trying to solve. Okay. F minus L gradient, but we need to define L to be a variable. We haven't done that. Let's define L. Defining L as a symbolic variable. Now the values of L we will try to find out in terms of x and y, and we'll proceed like that. Solve in terms of x, y, z. And let us see. Okay, there is one small problem. So we cannot directly solve this f gradient. What is f gradient? What we have seen here. So f gradient is nothing but 2x minus. Okay, we will show this. That's a small. There is a small issue here. So g gradient. So f gradient is nothing but 2x minus 2, and f gradient, the components are 2x minus 2, 2y minus 4, and 2z minus 4, and g gradient is nothing but 2x, 2y, 2z. So when we ask for solving f gradient minus L into g gradient equal to 0, essentially we are asking for solving 2x minus 2, see these components, see this minus L times this is equal to 0 means that this is a vector kind of thing, this is a vector kind of thing of the same dimension. So 2x minus 2, this is f component, minus L times 2x equal to 0. That's what we are trying to see. We are trying to solve, right? So we need to take each and everything, each of these components we need to subtract. Okay, so so how do we do that? So we need to take each of the equations separately. There are three. So three components we have to subtract separately instead of f minus L taken. That is not going to actually work. So f minus L, we need to separately list all these things. Okay, we need to separately list all these things. So for that thing, what we can do is we can split it. We can split. Okay, I will show you something else. List. What is this thing? If I convert, if I take a list of all these things, where it go? List. So what is this list? F gradient minus L gradient, L star G gradient. So what happened is 2x minus 2 minus 2x is taken, right? 2x minus 2 minus 2lx is taken. This is what we want. So we will be using this. This is equal to 0 is also okay. 0 is also, even if you do not put 0, it will be automatically taken as 0. If you do not write 0 here, so we will change to this. Now, so the values are x equal to, we are solving for x, y and z. So we are getting an expression in terms of L, which is an arbitrary constant, which we don't know what exactly this is. X equal to minus 1 L minus 1, y equal to minus 2 L minus 1, z equal to minus 2 L minus 1. These are the values we are getting. We don't know what exactly this L is, but if we solve f gradient minus L times g gradient, we will be getting these values. Okay, let me update the whole document, the whole code in the Google document. So update. Please try. And now we got x naught, y naught, z naught as minus 1 by L minus 1, minus 2 by L minus 1, minus 2 by L minus 1 as the values, Now in the Lagrange multiplier technique, what we are supposed to do is we need to put this x naught y naught. This is actually a point. This is actually a point on the G surface, which is a sphere, and we put this onto the G surface and equate it to 0 and see what possibilities are there for L. That's what we are going to see. Okay, now the next step is put this x naught, y naught, z naught to G and solve for L. So here we got not L values, grid solutions, we'll say, instead of L value. Okay, now the solutions are, we are going to solve once again. G dot subs, we are going to substitute x equal to what is that first value? There is only one value here.
Minus 1 by L minus 1.
Yes, minus 1 by L minus 1, but what I'm thinking is that we have to put it automatically, not by not manually.
It's a first coordinate of grad solution.
Sorry?
So we can put it as grad. It's a first coordinate of grad solution. So we can put it as a grad solve of 0 because grad solve is already in G.
Okay, so grad solutions 0, 0, right? I think 0 because
just one first coordinate, yeah.
No, this is actually a list of lists. 0, 0, 0 RHS, 0, 1 RHS, 0, 2 RHS, right?
So it's just not a one, just a list, no, sir. Is it a list of lists?
Yes. See this.
Yeah.
That's a list of lists. 0, 0. Similarly, we need y equal to that's 0, 1 and z equal to that's 0, 2, and we are solving for just L. What do we get? We get two values for L, right? But is this correct? L is equal to, oh, but just 1 second, what we have done here, 0, 1, 0, 2, we are substituting G this is equal to G of x naught, y naught, z naught, that's equal to 0, that's right. This is equal to 0, 0, 0, we are supposed to G we have substituted x2. Oh, sorry, we have not substituted the RHS, right? We are supposed to take it. We are using the notations also that x equal to is also appearing. That's not the correct thing to do. Yeah, that's correct. L equal to 3 by 2 and L equal to 1 by 2, two values.
Can you just explain why the command is required?
Which command? See, otherwise, okay. Otherwise, what happens is you just have a look at this. What exactly this is? If you simply use this, what will happen? That's the last print. X equal to minus 1 by L minus 1. We only want this minus 1 by L minus 1, right?
Yes.
X equal to is a symbol. It's a symbolic expression. That's not required. We only need that value. Okay, that's fine. We previously kept that x equal to was also there. That's why we got a long expression, which was not actually what we intended. So we got two solutions. Now Lagrange multiplier. The last step is to substitute this L value to the already computed this what do you call x naught y naught z naught x naught y naught z naught in the sense that grade solution 0 0, solution 1 1, solution 2 2. We have found values for L. Now substituting L2. So once again, since there is only one value, but there are two L values, of course, for L value in solutions. Also, let us put x naught equal to this. We need to evaluate that consists of 1 by L minus 1, I guess, dot substitute. What are the L values that we got? We got L equal to 3 by 2 and L equal to minus 1 by 2. So instead of that, we want just L equal to, we want just 3 by 2. So once again, we need to substitute L value dot RHS. Y naught is this, Z naught is this. So this is one extremum value. One extremum is, let us try to see what exactly these values are. And extremum is this. Now we are looping through both this things, and now we try to evaluate also. Value of f at this extremum is f dot substitute. Actually, we are supposed to take the square root because we want to take the distance. So we can of course take that. X equal to x naught, y equal to y naught, z equal to z naught. We are supposed to actually take the square root of this thing. We have completed almost all these things. Let us try to see it in action first. An extremum, that is also not getting printed. An extremum is x naught, y naught, z naught. X naught is equal to the grid solutions 0 0. Oh, but R okay, in 0 0, what is that 0 0? Grid solution 0 0, that's minus 1 by L minus 1, I guess. So for that, to that, what we are supposed to substitute. Oh, but L equal to, we need to, sorry, L equal to is required. L equal to, substitute for what? That is missing. substitute at the place of L equal to. And next term is minus 2, minus 4, 4, 81, 2, 4, 4, 9. These are the two values. Maybe we can try to do a plot also to see if our conclusions are matching with this, the computations. Let's see the plotting. Of course, the distance is actually, we are getting it as a square. 81, that's a square of 9, and 9 is a square of 3. Therefore, the maximum distance is 9 and the minimum distance is 3. To minus 2, minus 4, and 2, 4, 4. So let us see if the plot to some extent justifies our calculations or not. Plot 3. So what we are supposed to plot first? So let us plot that 1 to 2 point first of all. Equal to point 1 to 2, color black, size say 50, because otherwise somehow that point seems to be really a small point. Now we need to plot the sphere. Since we have to plot a sphere which is an implicit equation, x square plus y square plus square equal to 36, we will use implicit plot 3D. Instead of implicit plot, we will use implicit plot 3D. G equal to 0 for the range x between 36, therefore minus 6 is enough. But anyway, the point 1 to 2, I don't know, is that point inside? So 2 square, so 4, 4, the point is set a distance of 9 from the origin, so it's outside the sphere, right? The sphere consists of all points within a radius of 6 from the origin. The point is outside the sphere. So x minus 6 y minus 6 in implicit plot 3D we need to specify z also, z minus 6 show p. Oh, sorry, minus 6, that's wrong. But where is the point? Have we not added the point? Is that point inside? Only minus 6 is appearing. Oh, 1 to 2 must be inside, right? That's a mistake. Sorry. That's actually a mistake. It's of course at a distance of, see, when we are going up to 6, the distance is actually 36. Not 36. Yes. It goes to minus 6, 1 to 2. So from x-axis, in the x direction maximum 1, x direction maximum it can go up to 6. So we need transparency. Sorry, it's inside. 0.5. So it will be like that. Seeing the point. The point is here. Now let us plot one more point to which the maximum axis. Okay, but both the points will look like same. That doesn't matter. Anyway, it's on the sphere. We may even draw a line from where to where, and 1, 2, 2 to this point. Have we already plotted something?
P plus, we have implicit plot in P plus.
Okay. Alignment problem? No, no. P plus equal to this is okay, right? This point is it's not to us. Oh, this is not, this here plus is not to us because this is the first time we are doing that. Here, what is probably the problem? Okay, one bracket is missing. Is it that? Okay, so this is the closest point. Here it is. This is the farthest point. The point is inside the sphere. Okay, so this is the line joining. So this is what we are getting finally. So what I have done here is I plotted the sphere, added the point 1, 2, 2. After that, added the point, added one point which is an extremum point, and added a line also from that point to 1, 2, 2. That's it. It's a comparatively long problem. Let me update the entire Google document for this. Done. I hope that now you will probably start, at least if you have not already done, appreciating that the abilities of SageMath, because if if we change that function simply f and g, most probably without too much of modifications, the problem will this particular the code that we have written will solve. Will try to find out all the extremum points, all the extremum values, right? And of course, if the point is that the value is maximum or minimum can be easily determined, provided that you compare the values of this f at x naught, y naught, z naught for the first time, and second time, if you compare these two values, you can definitely determine if these 2 points are at which point is going to be maximum, minimum. If you do this by our hand, how much time it will take? Now we have already drawn the graph also, without much effort, right? Just by observing, just by using the points, the coordinates that we have computed, we plotted the 3-dimensional graph also of this, and the extremum is also computed. can immediately change this point 1 to 2, but instead of writing 1 to 2 here, maybe had I written some PTS here and taken 1 to 2, I can substitute everywhere PTS instead of writing 1 to 2, because this is hard coded now. The number 1 to 2 is hard coded now, so if I have to change the point to something else, I may have to change it everywhere. But instead of that, it will be a good practice if I defining a point to be just 1 to 2 as a tuple, and use everywhere wherever 1 to 2 is appearing as just PT. The problem will become more general in that way. Of course, here we have minus x, minus 6, 6, minus 6, 6, etc. we have taken, considering that we are actually considering a sphere, but that also can be given on the top, right? The ranges can be given on the top, so that we don't have to modify the problem after initializing with the first few variables. We can depend on the same commands that we have written here for any other problem with 3 variables. Okay. Let me modify it slightly. The Google Doc. With whatever PT notation I have introduced just now. That.
So,
Yes, please.
can we extract the points from the vectors like first coordinate, second coordinate, and so on, the way we do for the objects in list?
I didn't understand what exactly it is. Extend means you want to extend it for
Extract, not extend, sir, extract. As in, from the list we can extract the first member, second member, and so on. So from the vector also can we extract in a similar way? Can we remove the coordinates in a similar way?
extracting from where? From
Like,
solution.
like for example, suppose I define a point as a vector 1, 2, 2, and if I want to remove the first coordinate from this point, can I use any command? Like for the least, we can mention like which place it belongs to. The first element can be considered as a p of 0.
For capturing the element, you can of course use p of 0, p of 1, p of 2, etc. But you cannot modify it. A vector cannot vector object cannot be modified. What you can do is you can convert that into a list, modify it, and convert back to it back to a vector. For example, if you are defining v to be equal to vector 1, 1, 1. So if you use a v of 0, if we ask to print v of 0, this will print the value 1. But you cannot assign anything. V of 0 you cannot modify if that's what you want. But here v of 0 is working. I don't know. Let me see.
So the reason I'm asking is that if this is the case, then we can also generalize the function f, where we are putting that x minus 1 x minus the first point whole square plus y minus in f.
Here.
Yeah.
Right. See here. See why do you want to just take x minus instead of x minus 1? Why do you want to just change it to some other? Okay. What you are saying is instead of pt, right?
Yes.
PT
yes,
0.
correct, sir.
Yes. That is quite possible. That's not a difficulty.
Okay, fine, sir. Yeah.
That can be done.
Yeah, sir. My doubt is clear.
So PT that's 0. Just use PT 0 here. That's quite possible. That's not a problem. So what I'm saying is f need not be actually the distance function, because f can be any function which we are trying to optimize. So you can if it is a matter of just changing one line, it doesn't actually matter if you use PT 0, PT 1, PT 2, because we may not be trying to do that for a PT or something like that, right?
Yes, sir. The curve may be different.
Yeah.
I got it.
Here it's actually a distance from one particular point. That's why you are trying to think about x minus pt0, y minus pt1, etc. Problem can be completely different. So that may not help us in that situation. So instead of that, what we can do is that we can completely redefine this stuff. It's a matter of just redefining it at only one point. See, whenever we are trying to generalize the technique to be applicable for many problems, what we are doing is, at the time of definition, if you are making some modification, at one particular point, if you are trying to evaluate, if you are able to change these 2 points and solve it without altering the code below that, that's more than enough for us. Okay, so essentially we need to draw a line here, right? We are drawing a line here in such a way that we don't have to modify anything below this line. Okay, the problem will be completely, the technique that we are employing will be completely general in that case. So we are only defining G, we are only defining F, that's it. Okay, after that everything will be automatically following. So if you are writing it, if you are writing code like that, then we can certainly say that we have written a program for solving any type of constrained optimum using Lagrange multiplier. If you have to modify it in between, that's not going to be a general problem, a general solution. So that's possible. So of course, the issue is that when you try to do some problem in that much of generality, you may have to take a lot of pain, unnecessary pain. So usually people will see there should be a compromise between the effort that you are taking, and if you are getting a very good output which is that much worthy, then of course you can try. But most of the time, trying to generalize too much is not really what you call profitable, is what I think. Because, for example, suppose that in the case of we try to generalize many things, right? So group is actually generalization of the set of all integers. Okay, so instead of trying to understand the theory of set of all integers, we try to understand theory of groups. Okay, that's profitable for us because there are many other examples where we can apply the properties of group. But now the category theory is actually what you call a much more wide generalization of groups, topological spaces, etc. But the difficulty in understanding the category theory is too much. So is that really worthy for someone who is trying to solve some problem? Is that really worthy to understand? Is that really worthy to write that much a general program for solving some problems? That's the only thing that we have to think of. Okay, there is a trade-off between the effort that we are investing and the output that we are getting. If the effort is not getting that much profit, even if you try to generalize, even if you try to write a general code, then we usually will not go for that. We'll simply go with, to some extent, we will try to generalize a general code. That's what we usually do. Okay. So now that Lagrange multiplier problem is it's almost completely settled. Now probably we will come back to, since we have some more time, we will probably come back to that vector related stuff, the tangent line kind of thing. I think we already have constrained optimization, we have already done composing functions. These things we have almost completed. Now we'll go to some vector calculus, find normal vector, etc. Okay, we are going back to vector calculus, finding going into the three-dimensional space related stuff. So what are we supposed to do for this? Vectors, projections. I think this is something that previously one of the participants wanted to understand, the projections. So for almost all these things, what is essentially is that we need to understand what exactly we are supposed to do. So for projection, what we actually need, find the, I'm just looking at the textbook to understand what exactly the definition of projection vector is. Okay, so suppose that we have a vector B, and suppose that we have a vector V. Now we want to project this vector V to vector B. That's what we want. Projection of V onto B, which essentially means that, so this is equivalent to suppose that we put a light on the top of the vector V, at the tip of that V, and suppose that the light is falling directly back to V. Okay, if the light is falling directly back to V, where exactly it's going to fall and what the vector is going to be. That's what essentially the projection is. Okay, we'll try to see, we'll try to do one problem. So the question is I'm copying and pasting from the textbook Howard Anden's calculus from section 11.3. I'm saying this because if you want to have a reference at that thing, you can have. 7 from this edition, I think it's the 10th edition. So the question is essentially this. Find the orthogonal projection of V is equal to I plus J plus K on B equal to 2I plus 2J, and then find the vector component of V orthogonal to B. This is the question. Okay. So let us try to draw these two vectors first of all. The V equal to and V equal to we need to represent it as I J K, which is 1 1 1, and B equal to 2 2 2 2 0. Okay, on the two-dimensional plane. Let's draw that first. Defining it first. Vector 1 1 1. We need to define it as a tuple. Now B equal to 2 to 0. Let's try to plot it. Oh no, so this is not necessary. Plot V. Now onwards we should P plus. Plot B in green and show both together. Both are appearing in the same color. Why is it like this? I don't know why is it coming like that. Maybe RGB color should I use? I don't know. RGB color with vector might be creating some problem. 0 0 1 or 0 0. So color in the RGB format. That's it. Will it work? Oh, even that is not working. But previously it was working, I guess, right? What was the command that we used yesterday? That's what I'm thinking. Vector some command like start at also I think we define. Okay, can I do, okay, let me just see. If I use instead of this. Will it work? P is this, P is we plotted. I think this way it's working, but the previous one I don't know why it's not working. Maybe this is the way in which we are supposed to plot a vector. Okay, then see sometimes it's behaving strangely. Some commands it may accept and some may not. So the only thing is that we have to randomly see. Okay, these are the two things. Two vectors. So one is a B vector. Maybe we can put some legend label V. And B. I think 3-dimensional, I don't know whether the legend label is actually supported. Probably not. I don't know. I don't exactly know. Maybe we can place some text around this vector. Text at which point? So what is the command for text at this point? V, will it work? P plus equal to
It is clear from the color also.
sorry?
It is clear from the color. I think there is no need for this legend label
Why?
because we have assigned colors.
But still that legend its option is basically because when we are writing the code, we clearly know that it's green and yellow. But when someone is seeing, it's not very clear.
Yes.
From the picture, it's not very clear. That's fine. That's why I'm trying to put some text, if possible. Okay, text coordinates we have to give and the value we are supposed to give. Okay, let us convert this into a list or tuple and V. Coordinates. Okay, let us just give 1, 1, 1 itself and see. At least that is working. Where is that error coming? P plus is equal to text. So why is that still giving? Let me just see once again. Okay, otherwise we will, that's not actually the correct thing to happen. Oh, I think I should use text 3D. I think that's what the documentation says, in 3 dimensions. even in text 3D, I am supposed to put, okay, I am supposed to put the text first. How I use the text first and coordinate is later, I don't remember. Anyway, okay, here it's coming. At least this is the partial solution. Certainly this is not a complete solution, so at least this is partial. So even here I can probably take tuple v. Will it work? Yes, it's working. So I think that's good enough to solve the issue, at least temporarily. So convert this into, even v itself, is it not sufficient? Yes, v itself is sufficient. No need to even, v itself is taken as a point. Where is b? Oh. Okay, b is appearing somewhere, but maybe I would have changed I would have slightly moved it to some other point. Instead of writing it at b itself, exactly at b, I would have changed it to some other closer point. Okay. Now, so we have plotted both. What is text we are supposed to do? We are supposed to find the projection of that, and the projection vector is nothing but it's v dot b by norm b square into b. That's the definition. Okay, projection of v. Projection of v to b is nothing but v dot b. So we have to take dot product. V dot product b divided by norm b square, divided by norm b square. This is a scalar into b, and now let us plot that also. Color black. I don't know, line style will work. Dotted and p plus, because otherwise it will, the previous things will be completely gone. Is there any such thing appearing here? Is the line style? I think so. It is probably dotted. I don't exactly know. Maybe we can change the thickness of this. We are dropping to b, right? So let us change the thickness of b. Thickness is equal to 3. Let us keep, this is already black. Since we are projecting, let us take it to be white and dotted and see. I think there is a okay, now it's again difficult. Some better color, not white. Yellow. Can we try control the opacity here? Or we can probably make this this thick instead of the second one thick, because it's already inside. So this we will be able to distinguish, I guess. Yes. So this is the projection that we have. The projection vector, you can see that we are perpendicularly dropping it down onto B. We are getting it as the vector. Okay. So this is the projection vector. If you want to print the projection vector, that also we can do. Of V to B. 110. That's it. Let me just update the entire code to Google document, which I have not done. Yes. So the projection can be computed easily. Fine. So now let us see one more small problem. This is actually drawing the projection, finding the projection and plotting it. Now we will see one more problem which we will continue tomorrow. Finding the, it's very easy actually. We will try to find, given the normal vector and a point passing through that, let us try to find the equation of the plane passing through that vector. So the definition is this. I'll copy and paste. So if it's passing through point x0, y0, normal to a vector. Equation of plane passing through x0, y0, z0, normal to n equal to a, b, c. The equation once again from Howard Anderson's calculus. This is his. So writing down the equation is quite straightforward, but the thing is that we need to plot the graph of the normal as well as the point as well as the plane itself. Okay, let us try to see that. So suppose that we are trying to find out such a thing. 317 and perpendicular to the vector n equal to this vector. Okay, so the equation is quite clear to us. So let us take this n to be a vector, n equal to the same vector, vector 4, 2, minus 5. We already have the standard equation for that, passing through the point 3, minus 1, 7. So let's take ABC to be this, or point to be this, passing through. Passing point is this. So if you want, you can actually use this, use the notation. I think you can straight away use A, B, B, C. Is this? I think this should work. I guess so. Yes, this also will work. If you write like this, it essentially means that take A to be equal to 3, B to be equal to minus 1, C to be equal to 3. This is also quite possible. Otherwise, if you write A, B, C, I don't really think that this will work. Oh, that's also working. Great. A, B, C. Yeah. ABC is this, N is this. Now equation of equation plane is this that A into x minus x naught, everything is so what is x minus x naught? Passing through the point, sorry, N is actually ABC, not, oh, that's a mistake, x naught. N is actually ABC. Y naught is a naught. So equation of the plane is the first part of n into x minus x naught, which is n 0. So we need to define x, y, z as variables, x, y, z. n x minus x naught plus n1 star y minus y naught plus n2 star z minus z naught, and the equation of the plane is, it's here. And if you plot it, we need to plot a into, this is equal to 0, right? This is equal to 0, we are supposed to plot. Let us try to plot even that. P equal to, let us plot the vector n first. N dot plot as green. What else we want? Plot point, right? Passing through this point. So this is plot 3D we used, or plot, just plot we used previously. Let's see. Just plot is good enough. I don't know. Plot 3D will, I don't know. We have to see that. Next is what the point. I think we used just point. Size is equal to 50. Now the last one is the surface. Implicit plot 3D. The surface is nothing but this equal to 0. But now we need to specify the ranges. So where is that point? 3 minus 1 7. So is it not? Let us take it to be minus 7 7 7. Minus 7 7. So y and z and this is the normal. This is a normal vector, but normal vector we have not taken to that surface. Normal, here it is. The point, where is that point? That point is not in the center because we have defined the ranges like that. The point is somewhere there. Point is here. Normal is here. And the plane is here. That's it. Let me update the Google Sheet, Google document with this. Updated. And probably we will stop now. If there are any questions, I can try to clarify, and otherwise we will try to. So what was the question previously that is being asked? Find out the tangent plane at one particular surface, right? We will try to solve that also. I think it's now it's more or less easy. So the only thing is that we need to find the normal to that surface. If you know the normal, now everything is automated. Okay, everything is in place. Only that normal is left. Normal to that particular point we have to find out. That's the only thing left out. We need to, I need to just check. I don't exactly know that how to do that. I might have seen that thing, but now I don't actually remember how to exactly do that. I will try to explain it tomorrow. So the feedback link I will copy and paste to the YouTube stream as well. Yeah, the feedback link also. So if there are anything that I can explain, please ask now. Otherwise, we will be stopping and meeting tomorrow.
Sir, my problem is resolved. Thank you very much.
Okay, you were saying about your that installation problem, right?
Yes, 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 sir. Yes, sir.
Okay, so
I went ahead, sir.
yeah.
I went ahead with 9.2 only. What you mentioned earlier that there's a clash between Anaconda and Sage was correct. So after uninstalling Anaconda completely, it started working.
Okay, that's actually a good information. I shall probably try to post it in some blog also, saying that if someone is having the same kind of problem, that SageMath crashing, one possibility is that some software based on Python is already installed and there is a clash between the path names assigned by that software and SageMath. I'll try to post that in some blog also, so that someone else also will be able to do this. Okay, thank you for the information.
Thank you so much for the help, sir.
Thank you, sir.
Thank you, sir.
So thank you very much. We'll be meeting tomorrow, and the YouTube streaming links I will update and post it to that program coordinator today itself. Thank you. Thank you very much.
Okay. Thank you.